Dr. Sayantan Shil and welcome to my YouTube channel. Today I will discuss about multiplexer, and this is the topic which I cover, that is what is multiplexer, then block diagram of multiplexer, then block diagram of 2 is to 1 multiplexer and what is the expression of 2 is to 1 multiplexer, then how we can implement basic gates and or not along with NAND, NOR, XOR and XNOR gate by using 2 is to 1 multiplexer. Now, what is multiplexing? Multiplexing means sharing a common channel. A multiplexer is a logical circuit that takes several inputs and allow only one of them at a time to get through the output. It has several applications. Multiplexer is used in data communication for several computers to communicate over a single line. Multiplexer is used in radio to select only one channel from many. It is also used for routing purpose for several computers. Now, routing of the desired data input to the output is selected, or you can say is controlled by select line, or you can say data selector. This is the block diagram of multiplexer. Okay. Now 2 is to 1 multiplexer, that means the block diagram of 2 is to 1 multiplexer suppose 2 is to 1 multiplexer, this is the block diagram. Now multiplexer, it obeys some relation. What is the relation? Suppose m is the number of select inputs and n is the number of inputs. Then it obeys the relation, that is 2 to the power m equal to n. That means where m is the select inputs or data selector and n is the number of the inputs. Suppose if m is 1, so that means 2 to the power 1, 2. So that means here if one select line is 1, then you can select maximum 2 inputs. If the m is 2, so that means 2 to the power 2 or 2 square, that is 4. So that means if the select line is 2, then you can select maximum 4 inputs, right? Now for 2 is to 1 multiplexer, that is suppose S is the select line. Now if S is 0, then this 0th position data has been selected at the output. Suppose this data input is I0. When S equal to 1, then this 1 position data input, suppose I1, that has been selected at the output. Okay. So this is the block diagram of 2 is to 1 multiplexer. And obviously it obeys the relation, that is 2 to the power m equal to n, where m is the select inputs or data selector and n is the number of inputs. Now we can implement AND gate, OR gate, NOT gate. These are the basic gates, along with NAND, NOR, XOR, XNOR by using 2 is to 1 marks using the expression. What is the expression? That is the expression of 2 is to 1 marks, that is you can say y equal to S bar I0 plus S I1 according to this block diagram. That means when S0, then I0 is selected. When S1, then I1 is selected at the output. Right? Now, gates. The first gate, that is the basic gate, AND gate. And we know the circuit symbol of AND gate, that is this one. And the expression of AND gate, y equal to AB, right? Now we can rewrite this expression AB plus A bar dot 0. Why? See, we know the expression of 2:1 marks, that is y equal to S bar I0 plus SI1. Now if we compare these two equations, then we can easily implement AND gate by using 2:1 marks. How? See, here if we choose the select line A, now when A is 0, so that means 0 is the input, and when A1, then B is the input, right? So that means when A0, then 0 has been selected at the output. When A1, then B has been selected at the output. So now that means we can easily implement AND gate by using 2:1 marks, right? Next, another basic gates, that is OR gate. OR gate, what is the circuit symbol of OR gate? That is A, B, and this is the Y. And we know the expression of OR gate, that is Y equal to A plus B. That means if any of the input is 1, then output is 1, right? Now we can rewrite this expression in this way, because according to the Boolean algebra, we know that B plus B bar, that is 1. And here B dot A plus A bar, because according to the Boolean algebra, A plus A bar is 1. Now we can simplify this expression. Right? Now we know again according to the Boolean algebra, that is A plus A, that is A. So AB plus AB, that is AB, plus AB bar plus A bar B. Now in these two we can take common A, that is then B plus B bar, and here A bar B. Now that is A dot 1 plus A bar B. We know the expression of twist to 1 marks, that is S bar I0 plus S I1. Now if we compare these two equations, then we can implement OR gate by using twist to 1 marks. How? See. So now that means here if we choose A as a select line, then when A0, then B is one of the input. and when A1, then 1 is another input. That means when A is 0, then B has been selected as the output, and when A1, then 1 has been selected as the output, right? So that is, we can implement OR gate by using 2:1 marks, using the expression. Next, the basic gate, that is NOT gate. Now, NOT gate, the circuit symbol of NOT gate, that is this one, and here only one input. So if A is the input, then Y equal to A bar. So the expression of NOT gate, that is Y equal to A bar. Now we can rewrite this expression, that is A bar dot 1 plus A dot 0. Why? Because we know the expression of 2:1 marks, that is Y equal to S bar I0 plus Si1. Now we can compare these two equations, and here A is the select input or select line. So now when A0, then this input is 1, and when A1, then this input is 0. It means when A0, then 1 has been selected at the output. When A1, then 0 has been selected at the output. So now that means we can implement NOT gate by using 2:1 marks. Next, the universal gate, that is NAND gate. Now the circuit diagram of NAND gates, that is this one. If A and B are the inputs, then we can write the expression Y equal to AB bar. Now De Morgan's law states that the complement of the product of the variable is equal to the summation of their individual complements, that is Y equal to A bar plus B bar. We can write this according to the De Morgan's law. Now if we simplify this equation, again we know according to the Boolean algebra, that is B plus B bar is 1 and A plus A bar is also 1, right? Now we can simplify this, that is A bar B plus A bar B bar plus AB bar plus A bar B bar. Again A bar B bar plus A bar B bar, that is according to the Boolean algebra, A plus A is A. So we can write A bar B bar. And now this is A bar B plus AB bar. So here in these two we can take common A bar, then B plus B bar plus AB bar. So now this is A bar dot 1 plus AB bar, right? So again we can compare this equation with the expression of 2:1 marks, that is S bar I0 plus Si1, right? So now we can implement NAND gate by using 2:1 marks. How? That is, if we select A as a select line, then when A is 0, then 1 has been selected at the output. When A is 1, then B bar has been selected at the output, right? Next, NOR gate. This is also universal gate. Now, NOR gate, what is the circuit symbol of NOR gate? That is A, B, and this is Y. And what is the expression of NOR gate? Y equal to A plus B bar. Now again, De Morgan's second law states that the complement of the summation of the variable is equal to the product of their individual complements. That means you can write this A bar dot B bar. Now we can rewrite this expression A bar dot B bar plus A dot, sorry, A dot 0. Why? Because we know the expression of 2:1 marks, that is S bar I0 plus SI1. Now if we compare these two equations, then we can easily implement NOR gate by using 2:1 marks. That is how, if we select A as the select line, when A0, then B bar has been selected at the output, and when A is 1, then 0 has been selected at the output. Next, XOR gate. What is the circuit symbol of XOR gate? This is XOR gate, right? And the expression of XOR gate, that is Y equal to A bar B plus AB bar, right? Again we know the expression of 2:1 marks, that is S bar I0 plus SI1. So now we can implement XOR gate by using 2:1 marks. How? See, if we select A as a select line, then when A is 0, then B has been selected at the output. When A1, then B bar has been selected at the output. So now here we implement XOR gate by using 2:1 marks. And then the last gate, that is XNOR. Now the circuit symbol of XNOR gate, that is this one, when this input is A, if this input is B, and this is the output. Now we know the expression of XNOR gate, that is Y equal to AB plus A bar B bar, right? Again we can compare this equation with the expression of 2:1 marks, that is Y equal to S bar I0 plus SI1. Suppose here I choose A as the select line. Fine. Then we can implement easily XNOR gate by using 2:1 marks. How? Suppose this is the select line A. When A is 0, then B bar has been selected at the output, and when A is 1, then B has been selected at the output. Thank you. Thank you for watching.